Hey guys, welcome back to Striking Studies. So today we're going to be doing gravitation part 4 and this is the last part and you don't need to wait for me to upload more on gravitation so you get the whole chapter anymore. So, like a nice person, I have made a full agenda on what we're going to be doing today, and this includes weight of an object on moon, why the moon does not fall on Earth directly, Kepler's 3 laws of planetary motion, escape speed, satellites, and fact of video. So let us begin. The weight of an object on the moon. So the mass of the moon is less than that of the Earth, obviously. So the gravitational force also theoretically must be lesser. Therefore, we can say, with all the calculations and strength we have, we can say that the weight of an object on the moon is 1/6 of its weight on Earth. And now, why does the moon not fall on Earth directly? Duh. Obviously, it will just fall on Earth because of the Earth's gravitational field. But no, it doesn't, okay? Because the motion of the moon is just like the motion of an object in a circular path. The velocity of the moon is directed tangential to the circle at every point along its path. The acceleration of the moon is directed towards the center of the Earth, and this acceleration is caused by centripetal force, which is supplied by the gravitational force between the Earth and the moon. Okay, now who is Kepler? This person you see the picture, that's Kepler, and he made 3 laws on planetary motion long ago because he did not have anything better to do. And these 3 laws are called Kepler's first, second, third laws, or law of orbits, law of equal area, and law of periods. So, law of orbits. This law states that each planet moves in an elliptical orbit with the sun at one focus. Law of equal area. This law states that the line joining the planet and the sun sweeps out equal areas in equal intervals of time. And law of periods. The square of the time period of a planet revolving around the sun is proportional to the cube of the mean distance of the planet from the sun, which basically means t square is directly proportional to r cube, where t is the time period and r is the distance from the planet between the planet and the sun. So, escape speed. It's not the speed you need to escape someone. It is the speed which an object or you needs to escape from the Earth's gravitational field. Not a person, don't worry. So, if you only meet this certain speed, the object will be able to escape gravitational field. Otherwise, it will fall back right onto your face. And this escape speed is represented by VE. And escape speed on Earth is 11.2 kilometers per second or 1.12 into 10 to the power of 4 meters per second. Next, satellites. A satellite is a body which constantly revolves around. It revolves in an orbit around a comparatively much larger body. And I'm sorry that the rest of the slide is blank, but ignoring that, orbital velocity of a satellite. This is the velocity required to put the satellite into its orbit. And this velocity is approximately 7.9 kilometers per second if it's near to the gravitational field of Earth. Time period of a satellite. It is the time taken by the satellite to complete one revolution. T equals distance covered in one revolution by orbital velocity. And if you do that calculation, you will find out that it's approximately 85 minutes. Now, a geostationary satellite, but it's just stationary, kind of. Like you feel like it's stationary because it revolves around the Earth in equatorial plane with the same angular speed as the Earth about its own axis as it is called geostationary, and it's also called a geosynchronous satellite. Geosynchronous satellite. And the time period of this is 24 hours and its altitude is 36,000 kilometers above the Earth's surface. So basically this satellite moves just like the Earth with the same speed of Earth. So it looks like it's basically attached to the Earth with a rod and it's just moving along. But it's not, don't worry. Now, polar satellites. This is the complete opposite of geostationary satellite. It orbits in north-south direction as the Earth spins below in east-west direction. As a result, this satellite scans the entire surface of the Earth. So basically, the satellite goes up and down around the Earth, and then the Earth also spins also. So then technically it covers the whole surface of Earth, and it can also see the whole surface of the Earth because they're going literally in complete opposite directions. And now we have the fact of the video. And the fact of the video is satellites collide. Like, what? I don't know why this is a fact, but then I found it surprising that satellites collide because I don't know. I just didn't expect satellites to collide. I thought they don't collide. By the way, this person who's saying I knew that, that's me. I'm saying I knew that because I knew that from the second I found that out. Which was a few minutes before I made this video, but never mind that. But still, it just never comes to your mind that a satellite collides. I just feel like satellites are invincible. They don't collide. They shouldn't collide. So this comic has been made by me only, and you can comment down below. By the way, this is the end of the chapter. And you can comment down below how this comic was, which I made with a lot of effort. And also don't forget to subscribe and press the bell icon so that you know whenever my next video will upload, which is Sunday 9 a.m. And click that thumbs up if you want me to know that you like this video and you want more like this. Bye guys!